Suppose that we're interested in comparing two different populations, independent populations, and we want to compare the means of these populations, right? But suppose further that we do not know the variances in either of these populations. In order to do so, in order to conduct any statistical inference here, we're going to need to make use of the t-sampling distribution. And we're going to be able to do this whenever our sample sizes are large enough from both of the populations, but where the variances aren't known. And so if we wanted to, for instance, construct confidence intervals in this setting, right, then we are going to need to construct these confidence intervals using these t-based procedures. So in order to form a confidence interval for the difference in population means, we can make use of the t-sampling distribution when the variances are unknown. The variances being unknown is going to be a far more common situation than the variances being known. And so the t-based confidence intervals are going to be more commonly applicable to scenarios that you might find yourself in. So what is the sampling distribution? What is the setup for the question that we're thinking about here? Well, we're going to suppose that we take x1 to xn to be draws from a random population. These are going to have a mean of mu x and a variance of sigma x squared. And so we'll use mu x and sigma x, the subscript x always denoting that it comes from the population distribution of x. Then independently of this, we're going to take y1 through ym to be from a separate population with a mean of mu y and a variance of sigma y squared, right? And so a couple of things to note here. First, we can have different sample sizes here, n versus m. Second, we are interested in sort of comparing mu x and mu y. That's our primary interest. But in general, we're going to allow these variances to be different from one another, but also to be unknown, right? So we're not going to know sigma x or sigma y squared. Now, if we did know sigma x and sigma y squared, and then if we have n and m both being large, or if these are coming from normal populations, then we can say that the difference in sample means is going to be normally distributed with mu x minus mu y as the mean, and then sigma x squared over n plus sigma y squared over m as the variance. If we're relying on this being sufficiently large sample sizes, then this is an approximate relationship. If these are normal populations, then this is exact, right? But this sampling distribution arises from the central limit theorem or from the normality of the populations. Now, if sigma x squared and sigma y squared are unknown, then we can't directly use this because we do not know the variance here. And so the natural thing to do is replace sigma x squared and sigma y squared by their estimators. We can take the sample variances for those terms, but as soon as we do that, we're no longer going to be dealing with a normal sampling distribution. We're then going to be dealing with a t-sampling distribution. So to form a confidence interval with the estimated variances instead, we're going to be taking x bar minus y bar plus or minus our critical value. The critical value is going to be coming from a t distribution, and we're going to say that it comes from a t new distribution here. We'll talk about that new parameter in just a moment. It's going to be the alpha over 2 critical value, right? And then we take the square root of our estimated variance. So sigma x squared over its sample size, sigma y squared over its sample size. Okay. In terms of the number of degrees of freedom, this new parameter here, it's given by this formula that we have here. And so to walk through what's going on with this formula, we take the estimated variance of x divided by its sample size, estimated variance of y divided by its sample size, sum those, and then square it. That's our numerator. In the denominator, we take the estimated variance of x over its sample size squared, divided by its sample size minus 1, and then plus estimated variance of y over its sample size squared over its sample size minus 1. Okay, and so then we take the ratio of these two different terms here, and that's going to give us how many degrees of freedom we require in this setting. Now, this expression is not necessarily the cleanest expression. It can be a little bit difficult to remember. It can be a little bit difficult to work out by hand. And so sometimes instead of using that correct expression there, we use the minimum of n-1 and m-1 as an approximation. So this is going to be a conservative approximation. You will find that this will be less than the true value, right? And so we're sort of being overly conservative, overly cautious, but it's a lot easier to compute by hand. And so if you're trying to do this to get a rough sense, we can use this minimum, but the exact correct expression is going to be given by our expression for nu up here. The same type of confidence intervals can be used to find one-sided or asymmetric confidence intervals by changing out the significance level that we're working with here. So instead of alpha over 2, we could use alpha or 1 minus alpha to get a one-sided confidence interval. But otherwise, the same general procedures are going to apply. So taking a look at an example here of this in application, right, we're dealing with a biologist who wants to understand whether there's an impact of this newly introduced invasive plant species on native wildflowers in the meadow ecosystems. And so what they do is they select a random sample of 64 wildflowers where there is the invasive species and 100 from plots where there is not the invasive species. Then what they find is that the mean height when there are is 15, the mean height when there is not is 20, standard deviation is 3 if there are the invasive species and 4 otherwise. And they want to find a 95% confidence interval for the differences in mean height between these different populations of flowers. And so what are we actually dealing with here, right? What are the values that we've observed in our sample? Well, we can take a look and say that we have a value of n, so our sample size from x, right? So n is going to have a value of 64. M is going to have a value of 100. We have x bar is the mean from our first sample here, and so that's a mean height of 15. Y bar is the mean from the second population, which is 20. We have our sample standard deviation being 3 in the first population, and it is 4 in the second population. Okay, and so then here we know that we're dealing with a situation with unknown variances. We only have the sample values, right? We want a 95% confidence interval, and so then alpha is going to be 1 minus 0.95, so 0.05 for alpha here. Okay, and so we can work this out as we would need to. In order to do so, right, we are going to want to take nu to be equal to that sort of expression that we have, right, the ratio of the estimated variances, plug into that formula, work that out, and then we know that the critical value that we're going to be dealing with is T nu and then alpha over 2. Okay? Plug into the formula from there. And so we can actually work out, well, how does this all sort of come to be from here, right? So we get that n is 64, m is 100, x bar is 15, y bar is 20, sample standard deviations are 3 and 4 respectively. Alpha is going to be 1 minus 0.95 or 0.05, right? And then if we plug into our actual formula here, we get our 3 plugged in for the estimated standard deviation, the 4 plugged in for the other one, and then the 64 and the 100 as the relevant sample sizes here. We work through, we find that there's 157.87 degrees of freedom. I will point out at this point that there's no problem with having a non-integer number of degrees of freedom. Normally, when you're dealing with the t-distribution, you're going to have integer degrees of freedom, so 1, 2, 3, and so forth, but it's totally okay to have non-integer values for that as well. So 157.87, we leave it exactly like that. If we want to then find our critical value, we're going to need to turn towards statistical software, right? So we want the alpha over 2 critical value, the 0.025 critical value from this distribution. If we wanted to get that using R, we can use the QT function, the quantile from the t-distribution. We want the 0.025 value, and for degrees of freedom, so df here is equal to 157.87. If you plug that in, you get negative 1.975 here. We then can plug into our actual confidence interval formula. All right, so we plug in our values for our estimated sample means. We plug in our critical value that we just worked out, plug in the estimated sample variances or sample standard deviations, and we work through and find that the interval is going to be negative 6.08 to negative 3.92. And so that's the interval for the differences in heights between populations that have been dealing with this invasive species and those that have not been dealing with this invasive species. So with all of that, we were in a situation where we were assuming that the variances, while they're unknown, are actually different between these two populations. That's going to be a reasonable assumption in most settings, but every once in a while we're going to have a little bit of extra information, and we're going to be willing to use that extra information to say these populations should actually have equivalent variances. And when we're in that case, we can actually change the procedure that we're using slightly. We're still going to be using a t-sampling distribution, but we can combine all of our information together to get a single variance estimate. And when we do that, we're actually changing the specific sampling distribution that we can use. And so if we're willing to make this assumption that the variance of x is equal to the variance of y, which is equal to some common variance, then we can use what we call the pooled variance estimator instead. And so the pooled variance estimator is a way of pooling together information from x and y into a single estimate for our variance, right? So we call it SP squared. The P here is for the pooled variance estimator, right? And what we do is we take n minus 1 times by the variance of x, m minus 1 times the variance of y, those are the estimated variances, and then scale that by n plus m minus 2. Okay. What we'll do is once we have our pooled variance estimator here, right, we can replace both the estimated variance of x and the estimated variance of y by this in the formula for our confidence interval. Now, in addition to changing the actual variance estimate, we can also change which sampling distribution we use. So we then use a t n plus m minus 2 distribution rather than the t nu distribution that we were seeing before. Right? So we're changing both how are we estimating the variance, but also what is the actual sampling distribution that we're going to pull critical values from. If we make these changes, then we can plug into the same formula again. We get the difference in our sample means plus or minus our critical value, noting here that it comes from the n plus m minus 2 distribution, and then multiply by our estimated standard error, right? And so it's the same thing, except we've plugged in SP squared instead of SX squared and SY squared. Okay, so otherwise exactly the same interval here. Now, the important thing to note about using a pooled variance estimation is that in order to justify using this, we need to be willing to assume that the variances of the populations are actually equivalent to one another. This has to be an assumption that you're making on the basis of the subject matter or from the context, rather than on some statistical assessment. We need this to be coming from a situational assumption rather than testing the data to see if this actually holds. Turns out that if you are trying to use the data to inform whether you think the variances are equal, and then you go ahead and perform the test, that's actually not going to perform well as a hypothesis test. So if you can justify this based on the subject matter, then go ahead and use these assumptions. Otherwise, if you're not sure, just assume that they're different. Because if you assume that they're different and they turn out that they're the same, you lose a little bit in terms of the power of this hypothesis test, but overall the test is still going to work pretty well. However, if you make the assumption that they actually are the same and they're not, then it's going to perform a lot less well than the test would if you had assumed that they're different. And further, if you test whether they're the same and then perform this hypothesis test, then that's not going to give you a valid hypothesis test procedure either, right? And so this really has to come from subject matter expertise. And if you have that, then we can use our pooled variance procedure here. The other thing to note is that the same type of intervals can be formed to be one-sided or asymmetric by changing out which level we're using for the critical value. So looking at an example here of when this might be sort of applicable, we have a psychologist who wants to understand whether sleep deprivation is going to impact cognitive performance. So they take a group of 36 individuals who are sleep deprived and administer this Stroop test to them. They score an average of 15 with a sample standard deviation of 4. The second group of 49 individuals, these are non-sleep deprived individuals, are taken with an average score of 22, standard deviation of 3. Now, because the test is actually standardized, this Stroop test is a standardized test, the researchers assume that the population variances are equivalent. And so here, they're making the assumption of equivalence based on the standardized nature of the test, right? And so this would have to sort of be justified by knowing the behavior of this test across varied populations, but perhaps because of the standardized nature, they're willing to make that assumption, right? And so that's coming from the subject matter, not from some sort of statistical testing on it. So with all of this, we can collect the information that we have here, right? So we're told that there are n equals 36 individuals. Their corresponding sample average is going to be 15. Their corresponding sample standard deviation is going to be 4, right? Then we have m is equal to 49 individuals. Their average is going to be a 22, and their standard deviation is a 3. Okay. We know that we want a 99% level of confidence in our confidence level, and so this is going to turn to a level of significance of 1 minus 0.99, which is 0.01. Okay, and so with our 0.01 level of significance here, then we can work out what our critical value is going to have to be. The other piece that we're going to need to work out is what is our pooled variance estimate, right? And so this is going to come from n minus 1 sx squared plus m minus 1 sy squared over n plus m minus 2. And then we're going to ultimately draw from the t n plus m minus 2 distribution. And so then pulling this all together, we plug into our confidence interval formula and then can work everything out from there. And so we can take sort of all of this, actually plug in and see what results do we get. So we're extracting out this same information here. We get an alpha value of 0.01. If you plug into our pooled variance estimate here, right, so we're plugging in our 4 and our 3, our 35 and our 48 for our sample sizes, then we get that the pooled variance estimate is approximately 11.951. If we go, the relevant t distribution is going to go from n plus m minus 2, right? So 36 plus 49 minus 2 gives us our 83. So we're dealing with a t83 distribution here. Then we can work out, well, what is the critical value here? We want the 0.005 critical value because we're taking alpha over 2 and alpha is 0.01 here, right? This gives us negative 2.36. And this is going to be able to be gotten using the R function here. Right, and so with this R function, what we're thinking about is QT, taking QT of 0.005, right? So our level here, degrees of freedom is 83 because we're dealing with the T83 distribution. Okay, so that's all going to give us our negative 2.636. So then we can plug into our confidence interval formula here. We have X bar minus Y bar. We're going to be plugging that in as 15 minus 22, plus or minus the critical value times by our estimated standard error here. Okay. Note that we're putting in the 11.951, which is our pooled variance estimate, inside of the bracket because we don't have SP, right? SP is going to be the square root of 11.951, and so we can put it inside of our square root here. If we work through, that gives us this interval of negative 8.794 to negative 5.206. And so that's our 99% confidence interval for the difference in performance between individuals who are sleep deprived and not sleep deprived on the Stroop test, assuming that they have pooled variance. So whenever population variances are unknown, we need to make use, and we want to form confidence intervals, we need to make use of t-based confidence intervals, because as soon as you're plugging in the estimated variances into those confidence intervals, the relevant sampling distribution is going to be a t-distribution. We have a different result whether you're willing to assume that the variances are the same or if they're different between these two different populations here, right? If you're assuming that they are the same variances, this needs to be justified on the basis of subject matter expertise, and the conservative assumption is going to be that they are actually different. So if you're not sure, you should assume that they have different variances. From there, we can plug into t-based confidence intervals to work out what is the actual confidence interval for this parameter and conduct the inference regarding these two independent populations through those sampling distribution results.